has to do with the details about action potentials, which are nerve impulses, which cause nerve impulses, I should say. And those are the actual signals that are conducted by the axons in those neuron cells. So first, a little bit more detail about what membrane or resting potential is, and they're the same thing. It's when you have the cell or the membrane being polarized. So what does polarized mean? It means that there's a difference in the cell membrane potential. So when I'm talking about like potential, I'm talking about that there's a difference of ion concentration in the cell and a difference outside the cell. That difference causes the cell to have potential. Those ions have the potential to move in or out. Once that happens, there's going to be a nerve impulse. So typically speaking, when the cell is resting, it has a high concentration of sodium outside of the cell. This is something you should memorize. It also has a high concentration of potassium ions inside the cell. Now, these ions carry charge. Again, we're not getting into the formulas and the math behind it in terms of how are these actually calculated, the resting potential, but knowing the concentrations, putting them into a formula, normal resting potential for a neuron cell is from negative 30 millivolts, volts is a unit for voltage, to negative 90 millivolts. So that's pretty standard. If that changes because the ions are on the move, whether it's going in or out, then there's going to be a nerve impulse. And the action potential is going to change. And I'll get more into that in just a moment. So now, how is the main concentrations, how are they maintained when things are the cell is at rest? And I believe I mentioned this on the last PowerPoint. The concentrations at rest are maintained by those sodium-potassium pumps. We know that there are ion channels in which ions can move in and out of the cell. Those ion channels can close. So sodium channel, even though there's a lot less of those in the cell membrane, when we have resting potential, typically those sodium channels are closed to maintain the high concentration of sodium outside the cell, to maintain that negative 30 to negative 90 millivoltage rest. The cell is just being a cell. It's not going to be sending that nerve impulse. So now, what causes a nerve impulse? Yes, it's going to be a difference in those concentrations, but there has to be some sort of a stimulus, something that causes a change in that normal negative 30 to negative 90 potential. When this happens, the neuron membrane depolarizes. So now there's going to be a change, and it's an all or nothing response. So what ends up happening is, or what could end up happening, is that the sodium channel opens up. When the sodium channel opens up, hey, sodium is going to come into the cell, because remember, there's a lot of sodium outside. Normal diffusion going from high concentration to low concentration naturally when that gateway is open. As soon as that happens, sodium comes in, then the cell inside is going to be less negative, because now like we got a lot of these positives coming in. So we're less negative inside, so there's a change right there in the charge or voltage. There's going to be more positive inside, and a overall reduction. If you're getting more positive from that negative 30 to negative 90, there's a reduction in membrane potential when the sodium channel opens up. That has a name, which I think is on the next slide. It's called depolarization. So please make sure you know that. Now, the other thing that can happen is, well, maybe it's not the sodium channel opening up, maybe it's the potassium channel opening up. When that happens, again, there's tons of tons of potassium on the inside of that cell. So the gateway opens up, ions typically move, molecules typically move from high to low concentration, so they're going to leave the cell. When that happens, the inside of the cell, because now potassium's on the way out, it's a positive ion. The inside of the cell, again, there's going to be a change in that voltage. The inside of the cell does become more negative. That also has a name. It's called hyperpolarization. Okay, so here is an important graph when it comes to action potential and resting potential and what the actual millivolts are in these different phases. And it's showing you the graph in the middle, and I'll show you a bigger graph on the next slide. Please look over these little mini diagrams, understand the terminology, and understand what those channels, those ion channels, are doing at the different states on this graph. So first, we have the resting state, so bottom left. At the resting state, if you really look at the diagram, you'll see that inside the cell is more negative. Outside the cell is more positive, and the sodium channels are closed. And potassium is able to come into the cell. And please remember where the charge is the most negative versus positive. So the negative is being maintained by this scenario. And what's not being shown are those sodium-potassium pumps. Again, bringing potassium in 2 potassium ions for every 3 sodiums out. Okay, so this is at rest. We're at a negative, let's say 60, I don't think it's 60 looking at the diagram, but the range is from negative 30 to negative 90. So maybe we're in the, negative 60 range at rest. Okay, next, for depolarization. So looking at the diagram, sodium is able to come in, making the cell inside less negative or more positive. That's saying the same thing. And that, again, is called depolarization. The third diagram up at the top left, most of the sodium channels are now open. Whereas in the second one, maybe just some of them, open and just a little bit of sodium comes into the cell. Now, for phase 3, most of them are open. So that's like very quickly making the inside of the cell more positive or less negative, as you can see by the positive symbols underneath that bilayer, and then the negative on the outside. So now we have it's called the rising phase of that action potential. Next, for part 4, once action potential has been reached, again, a signal that's conducted by the axon nerve impulse, as soon as that happens, the sodium channel gets plugged up by another molecule. So sodium is not going to be moving through that channel any longer. And now the potassium pump is open, and potassium is going to leave the cell. So again, at this point, we have a higher positive outside because of that. And then finally, the very last stage, sodium is still not able to move, but that plug is no longer there. It's just a molecule that stops the channel from operating. That moves out of the way, but still sodium is back to being closed, that channel. And potassium is going to keep moving outside of the cell, again, to better balance out the resting state, get it back to the resting state. Something I almost forgot to mention is that at that undershoot, part 5 in the bottom right-hand corner, a lot of potassium is leaving the cell, so the membrane potential goes a little bit lower, a little more negative than what's normal. So if the normal membrane potential at rest was at a -60, then in this case, that number is undershot. So you might have a -70, a -80. And then what ends up happening is after that, the potassium channels eventually close, and then it goes back to regular membrane resting potential. Moves down a axon or down the neuron is being shown in the diagram in 3 different parts or phases, showing you how that action potential shifts from the left to the right. So looking at step 1, action potential is reached. To remind you of what action potential is, it's the actual impulse. So going back to hopefully remembering what that graph looks like, the sodium channel is opened. And sodium there's like an influx of it going inside, which causes a change in the millivolts, a difference in voltage. So then part 2, the action potential, it's shifting downward. Okay, it doesn't all happen at once. So, and it's very quickly, but it then shifts where, again, right next door, the sodium gates open up, sodium has an influx. For part 2, because it's shifting, like the cell, the membrane, it needs to get like back to normal. So now the sodium channel is now opened up, and to kind of balance out, get the cell back to normal, get it back to the membrane resting potential. So then potassium moves through, getting that normal negative on the inside. And then when you look at part 3, the initial beginning where that action potential was is now back to the resting phase, a negative on the inside, positive on the outside. And then the action potential has shifted towards the left. Again, influx of sodium inside, right where that action potential just was. Again, the potassium needs to cross over and go out to kind of balance that out and get it back to the resting phase. So again, it's almost a little bit like a domino effect, I guess. Action potential is reached, then the falling phase of that, getting it back to the resting state or back to membrane potential, normal membrane potential, negative inside, positive outside. Another video that you should watch, it's in Mastering Biology. Extremely quick along the axon. A few things that allow for that quick movement are the fact that outside of that axon in that neuron are lipid cells, and lipid cells are not good conductors. It's like they're insulators. They insulate our body and keep energy in. So there's lipid cells that go on the outside of that axon that keeps that pulse, that, again, that impulse. It keeps it inside, moving it where it should go. The other way in which a neuron is able to go really, really quick in terms of its conduction or impulse is by being thick. So the thicker the axon, and the book uses a really good example, I think, talking about like a water pipe or waterway. If you have a thin pipe and you've got water that needs to move through it, when it's thinner, it's not able, the water isn't able to flow as quickly. Then if you extend or make that diameter bigger, so it'd be like a bigger pipe, water is able to go through really quick. So having thicker axons also allow for that impulse to move quick. Another way is by just having a myelin sheath. So the myelin sheath is, we see these in mammals, vertebrates, and it's also insulation. It's produced by a certain type of cell, glia cells, and these help to protect and insulate that neuron or the axon. Okay, so then other things that you should know. So the conduction speed is way quick, so 120 meters per second. So I'm sure you know what a meter stick is. So imagine 120 of them in 1 second. That's how fast again, that impulse is able to move. Now, what is saltatory conduction? This is where there's like little breaks in between the insulation. The little breaks are called nodes of Ranvier or Ranvier. So these do not have any of those cells, do not have any of the lipid cells. It doesn't have any of that myelin. It's like, again, like a naked axon. And the nerve impulse is going to move, again, down the axon, and it's going to jump. It's going to jump over those nodes. And this does speed up impulse, because as soon as it gets to it, it quickly jumps. And it increases that conduction speed of it moving through, that impulse moving through. And again, the fact that it's jumping is called saltatory conduction. So here you can see the impulse moving down an axon, which is not myelinated or unmyelinated, versus when there are those nodes of Ranvier or Ranvier, and how much quicker it actually gets to the synapse, which is down at the bottom. Something that you should also know is the fact that those nodes are depolarized. So opposites attract. It's able to move across very quickly because of a difference in charge.